Hello everyone, my name is Penelope Gehring and I'm a PhD student at the University of Potsdam, and I'm very happy to contribute to this nice online seminar. I'm going to talk about some joint work with Armando Cabrera Pacheco, Carla Zederbaum and Alejandro Penuela Diaz on construction of electrically charged Riemannian manifolds with prescribed asymptotics and controlled mass. This talk is split into 3 parts. First, I will explain or introduce some things about charge initial dataset with non-positive cosmological constant. Then I will give a brief overview on the multi-relation chain construction and explain the intuition behind this construction. And then the third part is on our generalization of the multi-relation chain construction in the setting of electrically charged Riemannian manifolds with controlled mass. In this third part, I will then use the first and second part combined to prove our main result. Okay, so let's start with the first part by talking about the Einstein-Maxwell equations. So let M bar be a spacetime, so a time-oriented Lorentz manifold, and this spacetime solves then the Einstein-Maxwell equations if it solves the Einstein field equations, which have here the Ricci curvature, the scalar curvature, and also lambda as a cosmological constant, which we here consider as non-positive. The cosmological constant is then related to the acceleration of the expansion of the modeled universe. This is now the left side of the equation, and the right side of the equation is then 8 pi times the stress energy tensor, where we here choose electromagnetic stress energy tensor since we're looking at Einstein-Maxwell equations. One can look at this differential equation on the whole space-time, but one can also look at it from the point of view of an initial value problem, where the initial value in this setting is an initial data set where we have M gamma as a n+1 dimensional Riemannian manifold, K as a symmetric CO2 tensor, and E and B as an electric and the magnetic field respectively. So E and B are then induced from a 2 form which is inside the electromagnetic stress energy tensor. So, and then just as more intuition, if you have this initial data set, which then also has to satisfy some constraint equations, what one wants to do is that one wants to evolve this initial data set in time such that one gets a space-time, and then the initial data set would be a time slice in the space-time, and of course the space-time should solve the Einstein field equations, and K is then the second fundamental form of this time slice inside the space-time. So let us have a brief look at the constraint equations. So the constraint equation in the setting of like 3 parts. The first 2 parts coming from the Einstein field equation using the Gauss-Codazzi equations, which includes the scalar curvature, some terms with the CO2 tensor, the cosmological constant, and also the 2 fields. And on the other side then we have terms with mu and j, which is the energy and momentum densities. We also have a third condition, which is that the 2 fields are divergence free, which is connected to the assumption that the charges should be conserved. Next to that, one can also have other additional assumptions on initial data sets. For example, the dominant energy condition, which is related to a physical condition, which I now not discuss. I just mentioned that this dominant energy condition then means that mu should be bigger or equal the absolute value of j. And another condition which is often used is that the initial data set is time symmetric, which means that k, or later the second fundamental form, vanishes, which one can see that the constraint equations are simplified a lot. And in our case, so we are looking only at a special case of initial data sets, which we will call electrically charged Riemannian manifolds, And for this we will assume that they are time symmetric and that the magnetic field vanishes. And then the dominant energy condition plus the constraint equation simplify to this following inequality, which we will then also call dominant energy condition, where we estimate the scalar curvature from below, or we require a lower bound on the scalar curvature from below, including the electric field and the cosmological constant. Note that if the cosmological constant is 0 and the electric field vanishes, then we have the condition that the scalar curvature is non-negative, which is a often used condition in general relativity connected to asymptotically flat manifolds, for example for the positive massium or the Riemann-Penrose inequality. Okay, so we will now stay in the setting of the last line, and one of the most important examples for us is the following lambda Reis-Nordström manifold, where we will choose 3 parameters m, q, lambda, where m is related to the mass of the manifold, q to the charge of the manifold, and lambda, as before, to the cosmological constant. The lambda Reis-Nordström manifold then is defined as r plus to infinity times the n sphere with the following metric depending on m, q, lambda, where g star is the standard one sphere on the sphere, and p, m, q, lambda is then this function written here, which exactly then contains the dependence on m, q, and lambda. Note that the roots of this function then are singularities of the metric. So for making sure that this metric is smooth, we then choose r plus at the largest positive root of this function, or if there's no positive root, we choose r plus simply as 0. And since we want to have an electrically charged Riemann manifold, we also have to choose an electric field, which we do here depending on q and again at the function, and this electric field is then only going into radial direction. And by simple computations one can see that this electric field is indeed divergence free, and also if one computes the scalar curvature one can see that the lambda Reis-Nordström manifold satisfies the dominant energy condition with equality. Okay, so now this one is a quite maybe big function, so let's talk about some of the examples where we reduce this function to special cases. So for example, we have the famous Schwarzschild manifold if we just choose q and lambda equals 0, so here in general dimensions. If we have q non-trivial, then we have the Reis-Nordström manifold, and if we assume q as trivial but lambda as negative, we have the anti-de Sitter Schwarzschild manifold. Sometimes in the literature one takes lambda equals minus n times n plus 1/2, which is kind of like a normalized version of the anti-de Sitter Schwarzschild manifold, which is helpful for asymptotics, and here also then normalizes the last part of the function, and also is good for like things like dominant energy conditions. But here we will keep lambda as an arbitrary non-positive parameter. Okay, so on this slide I just want to briefly talk about black hole horizons, which in our setting now, and as in the setting of time symmetric initial data sets, can be seen as follows. So we take an electrically charged Riemann manifold with an empty boundary, and we call the boundary and horizon if it's a minimal surface. So it's the mean curvature vanishes. Also, if we call horizon outermost, if for every hypersurface sigma that encloses a boundary, the volume of the hypersurface is bigger or equals the volume of the boundary. So if we look at this picture and red is a boundary, then you see we have like this foliation of surfaces, and all of the areas or the volumes of the surfaces should then be larger or equal to the volume of the minimal surface as a boundary. Here sigma also is just an arbitrary hypersurface enclosing partial the boundary, but what one can show is that if one has a minimal boundary and there exists a foliation of mean convex surfaces, then enclosing like partial m, then one sees that partial m has to be automatically strictly outermost, where mean convex means that the mean curvature is strictly positive. Okay, so how are these horizons connected to lambda rational natural manifolds? So I said before already that the roots of the function inside the metric of lambda rational natural manifold are the singularities of the metric. So if we take the largest positive root of PMQ lambda, which is the R plus, then intuitively speaking what one can do is one takes the metric and extends it to R plus in a smooth way. Then R plus is becoming the boundary, and then analyzing the behavior of PMQ lambda, one can then characterize the boundary as a horizon and even a strictly outermost horizon. And this is done as follows. So we have these three cases. So the first case is we have indeed we have a positive root, so it's the largest positive root of PMQ lambda, and we assume that the derivative of this function at R plus is positive. Then we call this lambda rational natural manifold sub-extreme, and the horizon or the boundary then is a horizon and is strictly outermost. The second case is that we have still a positive root, but the derivative is 0. So that means that we still have a horizon, but it's not strictly outermost. And this is called extrema. And then we have super extrema, which is considered non-physical because there is no positive root, so also no horizon. And in these pictures you can now see some examples for it, where I'm just plotting the graph of PMQ lambda for some parameters. And here we have in the first one we have extremality, where we have a positive root, but the derivative is 0. The second one is then sub-extrema, and the last one where there is no root, we have super extrema. Okay. And so let us just, for the case that we already discussed, for the main examples, let us discuss some criteria on sub-extremality. So in case of Schwarzschild, we see that sub-extremality is if we have positive mass parameter, and super-extremality if the mass parameter is non-positive. Then for the normalized anti-de Sitter Schwarzschild, we have the same behavior. And in the case of Reisner-Nordström, where the parameter q is not 0, we indeed have an extremer case where m, for the case of m equals to the absolute value of q, and then for m bigger the absolute value of q we are sub-extremer, and m smaller than the absolute value of q we are super-extremer. And in general it's not so easy to write down criteria for sub-extremality, but there are some facts that I want to share with you. First, some monotonicity of sub-extremality, in a sense that if we take lambda Reisner-Nordström with parameters m and q, and this lambda Reisner-Nordström is sub-extreme, then if we choose two new parameters where m tilde is not bigger or equal m, and q tilde squared is smaller or equal q squared, then the new lambda Reisner-Nordström manifold is sub-extreme as well. And if now the original lambda Reisner-Nordström manifold with parameters m and q is only extremer, then by choosing m tilde and q tilde in a way that at least one of these inequalities is strict, we see that the new lambda Reisner-Nordström manifold is then still sub-extremer, which kind of motivates that choosing, there's kind of like a turning point between sub-extremality and super-extremality, where like a kind of like a critical point. And this one can indeed see if q is not 0, then one can find a unique m that depends on q and lambda, such that if we take parameters m equals to mq lambda, then this lambda raised to natural manifold is extremer. If we take a parameter m bigger than mq lambda, then it's sub-extremer, and if we take a m smaller than mq lambda, then it's super-extremer. So these effects are quite useful for kind of controlling the sub-extremality of lambda raised to natural just by its parameters in a way. So next, I just want to give a really brief overview on asymptotics, total mass and total charge. I will not give any definition because I will not really need that later, but let me just summarize like the background theory. So depending on what kind of lambda we choose, we want to have different asymptotics at infinity. The asymptotics is related to the total mass of the manifold because the total mass can be seen as an integral over infinity. So the asymptotics of the, let's say, of the metric should make sure that the total mass of the integral is well defined. And for lambda equals 0, we assume asymptotically flat and then look at the ADM mass, where if lambda is negative, we are looking at asymptotically hyperbolic manifolds, what means that we are asymptotic to an hyperbolic space with the radius depending on the cosmological constant. And here you can see if we would have chosen lambda as equals n minus n times n plus 1 over 2, then this would be again normalized, so we would look at asymptotically hyperbolic manifolds where they are asymptotic to the hyperbolic space with radius 1, which is often seen in the literature. And in this case, one is looking at the hyperbolic mass. A similar thing is with the total charge, because this one is also an integral over infinity, and so we also somehow, since the integral is also kind of consisting of the electric field, one also has to assume some condition at E and infinity, and here I'm just saying, okay, E has to go to 0 sufficiently fast at infinity such that the total charge is well defined. I'm not being here more precise because we will later look at manifolds that are outside of a compact set isometric to lambda raised to natural manifolds. And lambda raised to natural manifolds are by definition, in a way, how the metric looks like, automatically asymptotically flat for lambda equals 0 and asymptotically hyperbolic for negative lambda. Also, we know that for lambda raised to natural manifolds, the total mass is equal to the mass parameter we choose. And also the charge, the total charge is equal to the electric charge Q as a parameter, which means that all our manifolds, if they are at infinity isometric to lambda raised to natural manifolds, will then also have total charge and total mass equal to the parameters of the lambda raised to natural manifold. So we don't really have to worry about the definition, at least not in this talk. Okay, so we now have the most things introduced, such that also I can state one important conjecture in general relativity, the Riemannian Penrose inequality, here now stated in our setting of electrically charged manifolds with non-positive cosmological constant. And here, so let me go through the conjecture. So we have this kind of electrically charged manifold, we assume it's complete and has a corresponding asymptotics. It should satisfy the dominant energy condition and also have a non-empty strictly outermost horizon. Then the total mass satisfies this inequality where the lower bound depends on the area of the horizon, the area of a standard unit sphere, the total charge, and also the cosmological constant. And then in this inequality, equality holds if the electrically charged manifold is isometric to the necessarily sub-extreme lambda raised to natural manifold with parameters equal to the total mass and total charge of the initial electrically charged manifold. note that we, in case of Q being not zero, we additionally assume that the horizon is connected. We do this because there is a counterexample to the Riemann-Penrose inequality for the disconnected case and non-vanishing total charge by Weinstein and Yamada. So we just included also already this known fact into the conjecture. So on this generality, this is still a conjecture, but let me just show you some results where this is already known, like some cases. For example, the first proofs given in the asymptotically flat case without charge for three-dimensional manifolds is by Huysken-Illmannen for connected horizons using the weak inverse-mean curvature flow and without this connected assumption by Bray using a conformal flow. Then later this was also generalized to higher dimension by Bray-Lee, Lam and Huang-Wu in different cases, and also Visconti-Curie and Curie-Weinstein-Yamada then adapted the inverse mean curvature flow approach and the conformal flow approach to include an electric field, like respectively. Then there are also results on the asymptotic hyperbolic case without charge for general dimensions, where Fico-Sarkovic proved the Riemann-Penrose inequality for the graphical case, which proved then was finished by De Lima Girau, and also other cases where, or other geometric cases were proven by Ambrosio or De Lima Girau, Luzzorio and Silva. And then in the another case where we now have asymptotic hyperbolic plus charge, Chen-Li Su proved the Riemann-Penrose inequality for graphs over lambda Reynolds manifolds. So all of these results together motivate that indeed this conjecture can be written down like this, possibly with some more assumptions, but it makes sense to write it down like this, at least at this point in time. Okay, so connected to the Riemann-Penrose inequality, I also want to introduce another notion of mass, which is the quasi-local mass, and then also the quasi-local charge. Quasi-local mass is in comparison, like for total mass, it's not for like measuring mass in the whole manifold, but only for measuring mass or computing mass in closed hypersurfaces. So we choose sigma as a closed hypersurface and then also consider the unit normal field to it. Then the quasi-local charge is normalized integral over the hypersurface, where we integrate over the inner product of the electric field with the normal field. And note, if you have a rotationally symmetric manifold, then by E being divergence-free, the quasi-local mass is constant along the coordinate spheres by the divergence theorem. And another, like for now regarding the quasi-local mass, we choose the notion of generalized Hawking mass, which is now giving at a quite big formula, where we have first the integral over the mean curvature, then here's a term with the quasi-local charge and the cosmological constant, and then of course the areas or the volumes of the closed hypersurfaces. And note, if sigma is a minimal hypersurface, so this term vanishes, then this term is very similar to the term we have here as a lower bound in the Riemann-Penrose inequality conjecture, which of course motivates also that, for example, in the Huysken-Illmannen proof, you use the inverse mean curvature flow and the monotonicity on the asymptotically flat Hawking mass, which is indeed also can be seen here if you take lambda equals 0 and no charge, and let's say n is equals 2, then this indeed becomes the original Hawking mass definition that is then also used for proving the Riemann-Penrose inequality. And if we, for example, take lambda negative and no charge, then we get the hyperbolic Hawking mass, and if we have no lambda but charge, then we get the charged Hawking mass. So indeed, the Hawking mass that we write down here then reduces to the Hawking mass that we already have defined in other results. Good. So I want to finish this part of my talk by telling you some connection between the quasi-local mass and the sub-extremality of lambda raised to natural manifolds. This is a little bit more technical, and here I also have to introduce another function, which is like an auxiliary function, which is kind of induced by the PMQ lambda function that is inside the metric of the lambda raised natural manifold. And using this function, we proved that if we take a closed minimal hypersurface in an electrically charged Riemann manifold, then we can take a lambda raised natural manifold with mass equal to the Hawking mass of this hypersurface and the charge equal to, or the charge parameter equal to the quasi-local charge of the hypersurface, and can characterize when this is sub-extremal, and this is sub-extremal if and only if this auxiliary function using with these parameters is positive, and it's extremal if the auxiliary function is vanishing. And note that this R sigma is the volume radius, which means that it's a number such that you can write the volume of sigma as the volume of the sphere times R to the power of n. And note also that this in particular says that the largest root of the function inside the metric of lambda raised natural manifold to the PMQ lambda is this R of sigma. So this is very helpful later if we want to construct some manifolds that are at infinity lambda raised natural manifold, because if we would take such a minimal hypersurface and then want to somehow glue it to a lambda raised natural manifold, then just by controlling the mass and the charge of this hypersurface, we can control that the lambda raised natural manifold we glue to it is sub-extremal or extremal. So it's kind of like a more local definition or local criteria for sub-extremality. And with this proposition, I want to finish the first part of my talk, and I'm happy to then continue with the second part of my talk in the next video. Thank you.